Good morning, everyone. I hope that everything is going well with you guys. I'm sure a lot of you, as I'm filming this, will be sat in an A-level biology exam. If you're a GCSE student, you'll be sat in your GCSE chemistry paper 2 exam, and I really hope that they're going well for all of you. Following on from the photo I shared this morning regarding required practical 10B for AQA students, I also wanted to go through required practical 10A, which is purification of an organic solid, because I do believe that one of these will come up on paper 3. I don't know why. I do have a feeling that it would be the purification of an organic liquid one, but I mean, in theory, they could put both on. And whilst I do think it's really important that you are all abreast of all of the required practicals, all 12 of them. I know some of them have already been assessed in the papers that have come up. I also know electrochemistry wasn't on paper 1, so I might expect a practical element to that as well. But these feel like big practicals for them not to ask anything about. Now, with required practical 10A, there have been plenty of questions where you've had to give the method that you can see that I've already written out here, where that might be a 6-mark question where you are describing how you would purify a crystalline organic solid. And as I'll talk you through in a second, those are the key points that you would need to give to get 6 marks in a question like that. But what you also need to be able to do for this practical and required practical 10B and lots of the other practicals is not only be able to give the method, but to be able to explain why we do parts of the method. And there's been a few questions for required practical 10A whereby it's given you a method sort of like this, and then there's been bits that have been underlined or bits that have been written in bold text, and then it's asked you to explain each of those statements or each of the phrases or why particular words are so important in this method. So that's what I want to do here. I'm going to talk you through the method itself, but then I'm also going to make sure that we understand why we do each of these steps. And then I also want to talk a little bit about percentage yield at the end, because it could be that the percentage yield is really low for an experiment like this, and I want us to understand why, but it could also be that your percentage yield is over 100% in an experiment like this, which obviously is wrong, and it's being able to understand why that can happen, and also be able to explain why in like an exam question. So we'll have a think about that as well. The other thing that I really want to say about this is I'm sure a lot of you had a go at a practical where you purified an organic solid, and I'm sure a lot of you did that with aspirin. That is a really common choice for schools to do, and some of you might even have gone to a university to do it in their labs, which will have been pretty cool. But what I want to say is don't just associate this method with aspirin, because there have been plenty of questions in the past papers whereby you've been purifying paracetamol or ibuprofen or other crystalline solids where they haven't even told you what the solid is, or it's been benzoic acid before. So I guess as much as, yes, it can be useful to think, oh, this is the aspirin practical, I guess I just wanted to make sure that you were aware that it won't always be aspirin. It doesn't have to be aspirin. It's any crystallization of an organic solid. So in terms of the method, we are going to dissolve the crude solid being sort of once you've made aspirin, for example, the aspirin that you've made would be classed as your crude solid, and then once you've purified it, then it would be your pure aspirin. So it's just designed as a term to sort of mean an impure version of the product that we want. So we're going to dissolve the crude solid in the minimum volume of hot solvent, and that's actually 2 marking points in one there. You get one for saying minimum volume, you get one for saying hot solvent. And we'll have a think about why those 2 parts are really important in a second. And then once you have dissolved your crude solid in your minimum volume of hot solvent, you're going to filter it hot. Now what I mean by that is you want to keep the solution as hot as possible, so you don't want to be pouring that through a clap cold funnel, because then your solution is going to cool down, and we'll have a think about what the problems with that is. So you want to kind of have a warm funnel, so that there isn't a massive change in temperature when you pour the solution through it, so that we can keep that solution as hot as possible. And then once we've done that, we will cool and recrystallize, and it might mention using an ice bath. You can certainly mention using an ice bath, and again, that is kind of like an important additional point that we want to be able to explain why an ice bath is a good idea. And then we're going to filter under reduced pressure, which is also known as vacuum filtration or Buchner filtration, and you do need to be also able to maybe draw what that would look like, or certainly be able to finish off a diagram. They might give you the Buchner flask with the sidearm, and you might have to label it and add the Buchner funnel on, and we can have a think about, I guess why that works. And then we're going to wash the crude solid with cold solvent this time, and again it's important it's cold and that we understand why we're going to wash it. We can also at this point compress the crystals using some cork, and again we can talk about why that's important. And then we've got to dry what will now be hopefully pure solid, pure aspirin, pure paracetamol, whatever. Dry it, and I guess in terms of what that looks like, you can put it in an oven, a drying oven, or I guess what I would probably suggest is dry by kind of getting some sheets of filter paper and just having your solid in between, and then just squeezing out all of the moisture, and obviously you're going to have to repeat that a few times. We can also have a bit of a think about as well, about how we would know how pure our solid is, and I guess the main way we would do that is melting point analysis, because melting points for pure substances are fixed at one temperature, whereas impure substances melt over a range of temperatures. But we could also do it based on appearance as well. So aspirin forms needle-like crystals, long, thin, white. If it's not very pure, it definitely won't be white. It'll be more like cream, off-white, and you won't get those needle-like crystals. It'll just be like blobby, which is the worst description ever. So I would say it's non-needle-like in an exam. But yeah, this idea that you won't get the fine needles being formed, it'll just be like blobs. I genuinely can't think of a better word to use. Except non-needle-like for your exam answer. So, dissolving the crude solid in the minimum volume of a hot solvent. Why is that important? Well, firstly, in terms of the minimum volume, we want to create a saturated solution. We want the solid to be dissolved and only just have it sort of packed into our solution. That is then going to be massively helpful when it comes to recrystallizing later on, because recrystallization as a process is a bit pants, for want of a better way of saying it. You don't often get all of the solid you've dissolved back out of the solution, but if you have a saturated solution, so you're literally on that sort of solubility curve of you've got the maximum amount of solid dissolved in that particular volume of solvent at that temperature, as soon as you then start to cool it back down, the crystals will immediately be coming out of the solution. There's not an excess of solvent there that means that as it cools down, there's kind of still spare space for that solid to be dissolved. So the minimum volume is really important because we want to create a saturated solution. And then hot solvent is important because solubility changes with temperature, and you would not be expected to specify what solvent you wanted to use. Mark schemes tend to be quite happy for you to say water or for you to say ethanol, but you wouldn't be expected to know which solvent would work for a particular crystalline solid. So solvent is fine to use here, and I know that potentially sounds vague, but you can just say solvent here. It's a case of you not needing to know what everything is soluble in. But it is going to be really important that we choose a solvent whereby at lower temperatures the solid is not very soluble, but then as we increase the temperature, we get a steep rise in the solubility of the solid in that solvent, so that at higher temperatures we can get a lot of it dissolved. So if you're explaining why hot solvent is important, you would want to be talking about the fact that solubility increases with temperature. So it maximizes, or we are maximizing the mass of solid that can dissolve. Because again, if we're trying to purify our solid, we want to make sure we're purifying all of it and that we're not losing some of it. If we don't dissolve some of it, then in the next stage, when we filter it hot, that's going to get lost. So from a yield point of view, a hot solvent is important. Then we're going to filter hot, which, like I say, just means making sure that the apparatus that we're using is not really cold, so that we don't have the solution cooling down immediately upon hitting like the funnel and the filter paper. Now, that is also, again, linked in with this idea of if we have a saturated solution and it cools down to any degree, you are going to get solid recrystallizing out of the solution. So we have to be able to keep it at the desired temperature, or we are just going to have solid recrystallizing out and then being lost. So that's why it's important to filter hot. And at this point, what we would be removing by doing this filtration are any insoluble impurities. So in these first two steps, we want our crude solid to be dissolved. We don't want the insoluble impurities won't dissolve, so that's what we're getting rid of. So we want the filtrate, we don't want what's trapped in the filter paper after this step. So why do we filter hot? Because it's going to enable us to remove the insoluble impurities. Once we've then done that, the filtrate in your conical flask will then be cooled so it can recrystallize. So at this point, we want the crude solid to come back out of the solution, to crystallize out of the solution. So by cooling it down, solubility is going to decrease with temperature. And again, if it's a saturated solution, any degree of cooling it down is going to mean that less mass can be dissolved. So that's the mass that would then recrystallize out into your conical flask. And so I guess the idea of using an ice bath is just to continue that cooling process so that we have the lowest temperature for our solution possible, so that we are increasing the amount of, or the mass of, the crystals that recrystallize. Again, from like a yield point of view, we want to maximize the yield of crystals from the recrystallization process, and it is a really naff process. So again, anything we can do to encourage recrystallization is very much beneficial. So the ice bath increases yield of solid that recrystallizes as the solution cools. So at this point, you will now have cold solvent in your conical flask, and you should hopefully have some aspirin crystals. And what you might also get told is that you can maybe like scratch the base of the conical flask during the cooling process, because that will then give like a nucleation point for the crystals to form. Now, once you've cooled it as much as you can and you think you've got as many crystals back out of the solution as possible, we're going to filter under reduced pressure. Now, by creating like a vacuum, what we're going to do is be able to suck all of the moisture through the crystals down into the Buchner flask. And then in the next step, when we then wash with cold solvent, rather than the solvent just sitting in and amongst the crystals, that solvent gets drawn down into the Buchner flask as a result of the vacuum. So that's why we would opt to do it that way. I guess it's also a bit more efficient than normal filtration because you do have that suction, whereas in normal sort of filtration in your sort of triangle or cylindrical, obviously, funnel, we're just relying on the solvent draining through like under gravity, but also you've then got all of your solid packed into that space in your filter paper, which is where the compressing with the cork comes in, because you're kind of opening up space between the crystals for that airflow to help draw out more of the moisture from them. So there isn't really a reason why we filter under reduced pressure other than, I guess, it provides that airflow to help dry out the crystals, to help bring the cold solvent that we're going to wash it with through, and that again is going to help to effectively remove as many soluble impurities as possible, I suppose. So yeah, cold solvent, removing the soluble impurities. But I guess the other thing that's really important about washing it with the cold solvent is that we don't now want our product to be dissolving. So we did want it dissolved in the solution earlier, which is why we used hot solvent. Now we definitely don't want it to dissolve, because otherwise it's going to pass through into the Buchner flask and again be lost. So the cold solvent will remove the soluble impurities and it will limit the I don't want to say the word amount, sorry, that was my pause. And then I was thinking mass or moles, but I'm just going to go with mass. So limit the mass of crystals that dissolve. And that's why your solvent choice is so important, because if you have a solvent where solubility doesn't really change with temperature, then you're going to get not as much dissolving when it's hot, but you're also still going to get some dissolving when it's cold. Whereas what we want is something that really doesn't dissolve in the solvent when it's cold, but then massively increases in terms of the mass you can dissolve when it's hot. So there's that. And then because we've obviously just washed it with cold solvent, we're then going to have to dry. If we want pure crystals, we don't want there to be any moisture on there, any solvent, whatever that is, whether it's water, ethanol, etc. So we need to dry to remove any solvent from the crystals. Now, in terms of percentage yield, because the recrystallization process is poor, and that's a procedural issue, not a human issue, your percentage yield could be quite low if you were asked to work out percentage yield in relation to an experiment like this. And if they asked you why, you would say because we don't necessarily get all of the crystals recrystallizing in step 3, but also you could have lost some when you filtered it hot. You could potentially have lost some when you filtered it cold, depending on your solvent choice. But I think the main one is the idea that we don't get all the massive crystals recrystallizing in step 3. However, the flip side of that is I have seen a question where they've said, oh, the yield came out as greater than 100%, or you've had to do a calculation where the yield has come out as greater than 100%. And of course that can't be true. How can we make more of a product in an experiment than is theoretically possible? Obviously we can't. So why might the percentage yield be greater than 100%? Well, you might not have removed all your soluble impurities here. You might not have removed all your soluble impurities here. You might not have dried the solid properly, so there may still be some solvent left on there from step 5. So any of those things would potentially lead to a yield of greater than 100%. Now I say potentially because it might just kind of counteract a little bit of the poor yield we get from recrystallization, but I think obviously they'd make a bit of a point if they were going to do that. Yield is greater than 100%. Why? either you haven't dried it, and I have seen a method where they've given you this and they didn't say dry, and then they asked you why the yield would be over 100% and you needed to clock, we haven't dried the crystals, so there would be solvent on there still, or potentially impurities still. So that's really important, I guess, to understand as well. And then in terms of how we would check the purity of our crystals, we would want to be doing melting point analysis. So you'd put some of your solid into a capillary tube, and then you would gently warm the solid, and you would be watching it through like a magnifying glass, and you would be seeing at what temperature it starts melting. And whether it then melts completely at that temperature, or if it finishes melting at a completely different temperature. So like I said at the start of the video, the idea is if you have a pure solid, that will melt at one fixed temperature. Whereas if you have an impure solid, it melts over a range of temperatures. And will start melting at a lower temperature than the data book value for the melting point. So I'm pretty certain the melting point of aspirin is sort of 136, 137. If therefore you were to do melting point analysis and you found that the melting point of your sample was, or it started melting at like 134 and finished melting at 139, that immediately is not pure because it's not melting at one fixed temperature, but it probably isn't that impure because that range of temperatures is quite small. However, if we were thinking about aspirin melting at 136, 137 and yours started melting at like 125 and finished melting at 145, then that's a massive range. So that's probably going to be really quite impure. So it's a bit more quantitative than just looking at appearance. But we still can't kind of give a level of purity in that kind of way. We can just say, oh, well, it should have melted at this fixed temperature, it started melting at a lower temperature and it's melted over a range, however that range is small, so it's going to be relatively pure, or started melting at a much lower temperature across a massive range of temperatures, that's probably going to be really impure. Okay, and then like I say, appearance wise, which would be another physical property, again, it's perhaps it's certainly not as good as melting point analysis because we don't get any sort of quantitative effect, like evaluation that we can do. But it's still definitely something that we could look at to know, is it lightly pure, is it not? This would be thinking, I guess, in relation to aspirin specifically. So we'll change that. Because again, you're not expected to know sort of the appearance of all sorts of different crystalline solids, but aspirin would be white and forms needle-like, so thin crystals. And thus, if we had impure solid aspirin, it would be off-white, or I guess cream, either of those. And then, yeah, I guess the way that I would try and picture it is just like a big splodge of like solid. It's not really solid, it doesn't really look like crystals, it'll just be like mush almost. But yeah, I would say off-white, cream, non-needle like crystals, if I was to explain that in an exam answer. And they're the things that I think are really important for us to know for this practical. So as I said at the beginning, please don't neglect any of your practicals. Yes, you might want to prioritise some of them, and I'd suggest these ones, and your electrochemistry practical, so the idea of being able to set up a cell, knowing your standard conditions, knowing if we're measuring a standard electropotential that the standard will go on the left, being able to do notation for that, which again is where the theory comes in, which, because there wasn't any on paper 1, I do think there'll be a fairly big question on that. The other practicals that I think would be very fair game would be the rate equations practicals, so RP7, because I know there was a rate equations question on paper 2, but I don't think there was a practical element to that. So that would be, or those RP7 practicals would be others that I would definitely prioritise. But yeah, it's definitely worth having an overview of all of them if you've got the chance to do so, alongside obviously doing some practice of your multiple choice questions. But do let me know if there's anything I've said today, guys, in this video that you need me to explain. Apologies that it was quite long, but hopefully that kind of is what you need to know for this practical. And I will try to get up some more videos over the course of the weekend, some multiple choice videos. I know the OCR paper 3 is a little bit different in what they do, so I'll try and get a couple of videos up on there as well. But yeah, take time for yourselves to rest after today if you've had an exam. And then know that the light is at the end of the tunnel is hopefully shining quite brightly at this point, and that you know, can push through this final last bit, because the end is very much in sight, I hope. So yeah, take care, all the best for your revision, and let me know what I can do to help. Catch you soon, guys. Bye.